favorite language, at the very least, it's going to get you thinking about languages. Because if your career has been in Java, or if your career has even been in C-derived languages, C++, you're going to find out there's a whole big world out there that's quite a bit different. Gives you different ways of accomplishing your goals, and many of them are quite fun. So we're definitely going to show you a language that lets you think about programming. So this is the symbol for Clojure. This represents pretty much all the marketing that Rich Hickey, the creator of Clojure, has ever done, is to get his brother to design a very cool logo. We've got a yin and a yang. We've got intermixing the colors represents the intermixing of Java and Lisp. We've got a lambda in the middle. It's very cool. Now, when people talk about their pet languages, their favorite languages, one of the first things they say is, my language is powerful. What does that mean? What makes a language powerful? I'm willing to take suggestions from the audience.
Expressive.
Expressive, okay, that's a good answer. You know, maybe fast, maybe concise, maybe runs well on small CPUs, maybe anything. Power is really in the eye of the beholder. It depends on your problem. So, you know, you might decide that assembly code is the right level of power for you, or Forth, or Lua, or some scripting language like Python or Ruby. Power is one measure. What's nice about Clojure is it doesn't just talk about being a powerful language, and I hope we'll show during the session that it is quite powerful, whatever that quite means. We're combining power with two other basic attributes, focus and simplicity. Now these terms also are a little bit fluid, a little bit hard to nail down, but simplicity is your ability to concentrate on just one problem at a time, and either other problems you might have when developing your code are taken care of for you, or they're just no longer relevant. And focus is your ability to stay focused on your tool, on your problem, without having to have the kind of distractions that we're so used to when developing software, especially Java software. We're so used to these other issues that we kind of expect them to be there. And we're in this sort of state of continuous pain. And then you switch to something where the pain isn't there and you go, ah, that feels nice. So my goal is to get you thinking in these terms and see how Clojure lets you work in power, simplicity, and focus. Now, at its core, Clojure is a functional programming language. And the joke is, well, other language must be dysfunctional. But functional in the mathematics term. So here is off of Wikipedia their definition of a function, and basically the core of a true function, a pure function, is that for whatever input x you put in, you'll get the same output y. And that's kind of nice. You know, this is talking about no side effects. The goal here is in a pragmatic way to get rid of side effects that can occur when you're running normal code. And the normal code that we write in Java is just full of side effects, especially if you introduce things like multiple threads. All kinds of havoc can ensue at that point. And Clojure goes in a very different direction that we'll see shortly to help ensure that that kind of thing doesn't happen, that it's simple, that you only have to think about a limited problem set and not the problem set that includes multiple threads and mutability and a bunch of other stuff. So say you're working on some kind of data-oriented program. Maybe it's tax return, maybe it's Obamacare or something like that. You start looking at this, you're like, oh, okay, well, obviously I'm building some kind of taxpayer type thing, and it's going to have all these different properties. And you say, great, you know what I can do is I'll go create myself a noun. I'll create myself a taxpayer noun, and I can express my system in terms of what this noun is and what it does. And you say to yourself, yeah, I've created a noun, I'm done, right? Actually, what you've done is created a whole bunch of verbs, okay, because you've locked up your data inside these getter and setter methods so that you have to write custom code in order to extract them. You've locked up your data nice and tight. And it ends up feeling in some ways like one of the old school adventure games where you get to a conversation point, you only have a limited number of options you can do. You get to do what the API tells you can do, no more, no less, no going off the track, no writing your own script. You're just limited. Clojure does it a little bit differently. Data is a very first-class citizen in the Clojure world. We start with the idea of data and then start talking about functions that can work on data. And I know the first thing that you might think when you see a screen that looks like this is, oh my God, Lisp. Okay? Has anyone here worked in Lisp ever, college, anything like that? Okay. You know, I did way back in college. Did a little Lisp for a semester or two. I've always treated Lisp and your ability to think in the Lisp way, highly recursive, as a good indicator of sort of overall talent to do software, but I've never done any serious work in Lisp until I started using Clojure. But Lisp is something special. You know, this is a little XKCD. At this point, yeah, 50 years old. People who use it become passionate about it. Guess that's not limited to Lisp. Have you ever hung out with a Pythonista? But I love the, you know, elegant weapons for a more civilized age. So this is Clojure code, and it differs a lot from Lisps in general. Clojure is a break from the history of Lisps. It's not common Lisp on the JVM. It's something entirely different, but it shares a lot of the syntax and a lot of the intention. Here we're defining a map. So Clojure has a built-in map data type. It uses the traditional curly braces, and it's keys and values. So the keys are the colon parts, the values in this case are mostly strings and other literals. We'll go into more detail on that in just a second. So here is one of our core basic data types in Clojure, and we have a single generic verb for modifying it. So whether we're changing the first name, changing the last name, or in this case adding an entirely new key value pair to the map, it's the same function. It's one verb to do all kinds of different potential work on all kinds of different potential data. And interestingly, one of the key principles of Clojure is that data is immutable. They use the more technical term persistent data structure. But it means that when we define our taxpayer, it is in its final state. It will never change. When we associate associate a new key value pair into it, what we actually get back is a copy with that change reflected in it. The original is left untouched. Now, that sounds inefficient. The implementation of these persistent data structures makes it quite efficient and not as memory intensive as you might think. Back to Alan Perlis, the guy who said you're going to be thinking about programming. He is full of these little epigrams, interesting, pithy sayings about software. Better to have 100 operations on one data structure than the more object-oriented style of having lots and lots of nouns and lots of verbs specific to those nouns. Now, Clojure is a kind of chimera. Chimera is a fantasy creature that combines several different creatures and ends up being a little bit more than all of them. So this is some kind of lion, snake, and I think a goat. Clojure is a lot of Lisp, so it's kind of working through that world of common Lisp that came before it, but it breaks with it in a lot of ways. It's also Java, so it runs on the JVM. It can be compiled ahead of time into pure bytecode, or you can ship the source code out at runtime, whatever you want, but it runs inside the JVM. It interoperates cleanly with Java code. So it gets all the benefits of the JVM, speed and reach, the ability to run on, inside a web browser if you want, all kinds of servers, all kinds of platforms. You can run Clojure anywhere you can run Java. But there's also some wiki abstractions because of that. So occasionally you're doing Clojure code, and I'll show you some examples of a little bit of ugly Java coming out of the woodwork. So Clojure is a language, Java is a language we're all used to, we all know it very well. What makes Clojure different than Java beyond just the syntax? In fact, what makes Clojure better? One of the first things about Clojure is that the full language is there all the time. What does that mean? Well, in the Java world, and C, C++, all those traditional compiled languages, we start with source files, and we run them through a compiler. Often this is built into our IDE or hidden from us, but beneath the surface we have a compiler, and it produces class files which contain the bytecode. And then separately, we run a Java virtual machine that can read that bytecode and start executing it, and then boom, we've got a web server, we've got a IDE, we've got some other form of application. But there's that clean separation. We do all the compilation, then we throw away the compiler, we throw away our source files, those aren't relevant anymore. Now we have our compiled class files and bytecode, and we can run with them. Clojure is a bit different. We have Clojure source files, yes, and they're structured and organized into namespaces, which are roughly the same as packages, much like they would be in the Java world. But Clojure actually runs inside a JVM, not as a separate compilation stage. It runs inside your normal running virtual machine. And it will read those source files as needed, and it turns them into bytecode, into classes and methods and all the other stuff that you need to run inside of the JVM. But interestingly, that's not your only option. Lisp originated the idea that is now much more common. We know it from Python, and we know it from Ruby, we even know it from JavaScript, of a read, eval, print loop. That is, read some input from the console, typed live by the user. Evaluate it just as you would if it was contained in a source file. Do whatever it takes, including perhaps creating new classes, new bytecode, whatever, and execute it, print the result, and go back for more input. That seems like a cool thing. Oh, great, I can try out some stuff. But it's actually a lot more than that. You can actually keep a REPL up at all times while you're building, and you get to not only try out your code a little bit at a time, but you get to run your app. You could modify existing functions on the fly. I do this all the time. So running app, I redefine a function within a namespace and keep going. And that's a very powerful way to develop. And that's not even using the debugger. That's just using the built-in features of Clojure and the REPL. Some people, when they're building a Clojure app, I haven't gone this far yet, they will open up a port in their running test server. You wouldn't want to do this in production. But they'll open up a port in their running server that allows you to connect remotely to the REPL. So in your live system that's being tested, you can go in, use the REPL to investigate what's going on, to live patch things if you want. It's a very powerful idea because the language is there all the time. The compiler comes along for the ride. It's essential at runtime that everything needed to compile is there.
In order to add open source to the existing Java project, does that just mean I need to close the jar to build off the GitHub in order to bring in REPL?
So the question is, in order to integrate Java code with Clojure code, what do you need? Okay, the other way around. So yes, I think the short answer is yes, Clojure is a jar from the JVM's point of view. To it just looks like any other Java library. But it has sort of entry points that you can reference for the command line or by your build tool. And it will look for Clojure source files on the class path and compile them on the fly if necessary. And there's also an ahead of time compilation option where you can pre-compile everything to bytecode, and it will pick that up in preference to the compiling the source, or even when the source isn't available. So you have those options. In reality, AOT compilation is fraught with a bunch of problems. It's something that's best only done at the very last step when building a final application that you want to deploy. Trying to AOT compile ahead of time has a bunch of issues that I could go on about offline. But still, read eval print loop is very cool. So we're going to see some Clojure basics, and maybe we'll see a little bit about how cool the REPL is for writing and doing code. Okay, so here I'm running IntelliJ. I'm using a plugin called Cursive that gives me really good integration with Clojure and Java and a nice REPL. So here's my REPL. And let's start kind of from the ground up. First thing any language needs is literal types. So a number is a number. So it read the number 1, or the character 1, evaluated it, so it turned it into a literal, the number 1, and printed it back out. Whoa, awesome. Yeah. Strings are Java strings. Okay, no surprises there. There's also, you know, any kind of number you can imagine should have 3. There's actually a ratio type. So if you say 22/7, that's not doing a division operation. That is, let me just fix that, there we go. That is actually what's called a ratio, and it stays as a ratio until you finally say, no, I need this as a float. So, you know, if you, we're jumping ahead here, if you multiply 22/7 by, say, 3/4 or something, you'll get with a new ratio. That's kind of cool, because why commit yourself to a limited resolution until you really need it, limited precision. Okay, so getting back to this. So you have numeric types, floats, ratios, you have strings, you've got true, and you have false, which evaluate themselves. You also have Java's null, which in deference to the world of Lisp is called nil. So Java null prints as nil. The Clojure REPL reads nil, makes it a null. Nil and null, exact same thing between the two. There's a lot of Clojure where they try to maintain fidelity with the underlying platform, which isn't always going to be the JVM. That's a discussion for a little bit. Next simple data type is the vector. A vector, actually no, we got another vector. We'll do keywords. A keyword is a special string that starts with a colon. The colon identifies it as a keyword. And it can be any text. So how about, you know, ace of spades. And it evaluates to itself. These things are often used, you might remember that example, as keys inside a map type structure, an associative structure like a map. And in fact, it's kind of interned, meaning that you know, behind the scenes there's now a Java object that represents colon ace of spades, and that Java object is the same Java object regardless of where, what namespace or what REPL you type in colon ace of spades. It evaluates the same object. They make really good keys because of that in structures. There's also symbols. A symbol looks like a keyword, but is just a word. Here's a undefined symbol, which turns into an exception. So it prints out a fairly long description of that. There's a lot of ones built into Clojure. For instance, there's a symbol for, oh, what's a common one? Deafen. Oops. Oh, okay. Odd little thing there. Let's try map instead. That's definitely a function. Okay. So map is a symbol. That symbol evaluates to a function provided by Clojure, and it has an odd way of printing it out that is not very helpful. Okay. Now the next type is the list. This is actually more traditional for a Lisp, is to have a list and it has stuff in it. Unlike languages that are very strongly typed, in Clojure your collections can have any type of data in them whatsoever. So here our list is the list of 1, 2, 3, 4, 5, and it evaluates and prints itself back out. Now the thing about the list is special. If you know anything about Lisps, you know that this is how you call a function, is you put a symbol inside parentheses, and then you supply some arguments. Sure. Okay. In that previous example, if I omit the quote, it's going to treat this as a function call and complain that something is going on. This is one of those leaky abstractions. There's apparently something called clojure.lang.ifn. We now know that numbers turn into a Java lang long. And what Clojure was trying to do is it's saying, okay, that first thing inside a list, that's something that I can execute as a function. So I'll cast it to this IFN interface. And that doesn't work because we forgot a plus at the beginning, and so we get an exception. Clojure is pretty well known for having terse and not always that helpful exceptions. So inside Clojure, we can define a new symbol. So let's define a symbol called our list. And we'll make it the list 1, 2, 3, 4. And now we can type, say, our list, and it evaluates, our list. It evaluates that thing we put in before. We can also define a map. So we'll define a map, and we'll call this presenter. And it'll be last name, newest ship, and first name, Howard. And now I can print out presenter. There's my data. And as we saw in that other example, I can associate into it a new key. So I can say with presenter, we'll say that the location is Orlando, Florida. But presenter itself hasn't changed. So we put that new key in there, and it hangs out. Now there's an interesting thing here. Maps. If you think about a map, it's kind of like a function. Because if you have a map and you provide it a key, you expect to get back out the same value. They're persistent data types. Once you have a map, the keys and values in it can't change. So anytime you ask for a key on a map, you'll get back the same value. In fact, a map is a kind of function. Its domain, which is identifies what values you can put into the function, are the keys of the map, and it outputs values from the map. And that shows up in Clojure, that you can use a keyword as if it was a function and pass it a map. And internally, the keyword says reaches into the map, pulls out the corresponding value, and returns it. So keywords are actually a special kind of function that work only when they're used with maps. And let me see, there's a vector type. A vector type uses square brackets. And you don't need to quote it because it's not, doesn't look like a function call because it's square brackets instead of parentheses. And there's also a set type. Whatever. So this is a set containing, in this case, a bunch of different keywords. So colon curly brace. Okay. Let's see. That's probably enough for now. We'll come back to more of this in a little bit. So the REPL is very powerful. And I can see I already forgot to, I was going to show you how to define a function and redefine the function, but just trust me on that. The REPL lets you do that. And this is kind of cool because if you think about how long it takes to do things, you know, sort of the 70s kind of way, which is, oh, I wrote some code, I'm pretty confident, put it in production, see what it does, that's a pretty long cycle between when you write the code and when you find out it's broken and when you figure out how it's fixed and then correct the bug and then put it back into deployment. Big, long cycle. Anyone in a shop that this looks like something you do ever? It's embarrassing for our industry how prevalent this still is. Maybe you have some proper integration testing. You know, you either have a command you can run before committing or a continuous integration server. So you do your check-ins and it does the checkouts and it runs them through some tests, and when they blow up, it sends you a few 100,000 lines of exception report. And you try to figure out what went wrong. But still, that's better than waiting for production. Maybe you've got some unit tests. You know, there's even tools that constantly, oh, my code changed. I'll rerun all the unit tests and see what we have. That's, again, much tighter, smaller circle. But all of those pale in comparison to just having the REPL open, where you can just see anything you need to see and test anything you need to test, either by defining formal tests or just doing an ad hoc test on the fly. And especially in the Java world, because what is Java really bad at? It's fast when it's running. It gets faster over time because of hotspot, but what is the worst thing about running a Java program? The startup time. You know, so, you know, I have thousands of tests for Tapestry, and I'm running them all the time, and but there's always that agonizing delay on my relatively fast computer to get a JVM spun up, to do the initial load of all the code, and to start running the tests before I can even see that green bar in test in JUnit or testng. Before I can see the green bar even move, there's a long delay. With the REPL, live all the time, it's completely immediate. It's like a whole new level of speed for development and testing and learning and understanding the code. Okay, pop quiz. This is something I made up, but it's not too unrealistic. Which of these parentheses, if any, can we get rid of? Maybe. You have to know stuff. You have to know a little bit about operator precedence and a few other things. And my answer is I don't know and I don't care. I don't know because I can never remember the exact operator precedence rules because they're all over the place in Java. I mean, even though there's like 40 years of history there, I don't remember them, so I'm not going to expect anyone else to remember them. Yes, I could probably get rid of some of these parentheses, and then the next person who comes along to maintain this code, instead of having code, they have a puzzle to work out before they can even figure out what it does. So that's the fun of programming. Hopefully that's not fun. If that's the fun in programming, I have been following the wrong path for a long, long time. Everything in you should see it with forth. There goes all your issues with structs. So don't know, don't care. This is roughly equivalent written in Clojure, and I've cheated. I've cheated badly because I've used idiomatic Clojure indentation, which helps you see the structure. And but even so, it breaks things up. And you can see Clojure tries to be more expressive. For instance, instead of using the C-derived pipe and double pipe for ors and ands, it's using word, or, and. And the core thing here is that Clojure doesn't have any operators, so there's no concept of operator precedence. All it has is this list structure for code. And the list structure defines the precedence directly. Okay, so there's never a question about operator precedence. It executes sort of top down and bottom in, and you're done. There's never a question. Other languages start seeming kind of baroque by comparison. And I'm specifically thinking about Haskell, but Java applies as well. So Uncle Bob Martin, great speaker. Oh, we're in Florida. You'd love him. He's a diehard Republican, very super red. You know, this is according to his. He noticed that you know, when Ruby came along, which was a much less capable language than Java, you know, loosely typed, dynamically typed, didn't have a compiler, ran kind of slow, and yet a lot of the best, brightest people in the Java space abandoned Java and switched to Ruby. I kind of missed that wave, so I'm happy to be on the, you know, hopefully the leading edge of the Clojure wave. But yeah, the smart people tend to find the tools that let them work most effectively, and those tend to be simpler, not more complicated. So let's talk about solving problems in Clojure, because that's what we do. We're programmers. People give us problems, we solve them. So how do I do anything in Clojure? Hint, you're going to call a function. Or perhaps you're going to define a function and then quite likely pass that function to some other function. Welcome to functional programming. Welcome to higher order functions. Everything's about functions. So how do you define a function in Clojure? You call a function. Technically it's called a macro, but it looks like a function. And def n, yes, see, define a function. Somehow we saved an F in the process here. Okay, so define, and first we provide a symbol so that we can reference this function later on, and we have a vector where we specify the parameters and have symbols for each parameter, and oh my god, that's boring. I'm not going to give you that example. Here's something a little more dear to my heart. I'm a game player, play all sorts of Euro games, some card games, occasional game of poker. Anyone recognize this? Cribbage, okay. One civilized person in the crowd. Yes, cribbage. It's a great pub game, and the pegs in cribbage are for scoring because you score a couple points here and a couple points there, so you keep sort of hopscotching or leapfrogging your pegs over each other. Now, basic thing in cribbage, I'm not going to go into all the details of the game, is at the end of pegging, there's a scoring round, and each player will have 4 cards, and they're going to score points based on different patterns and combination in those 4 cards, plus the shared flip card. So there's a flip card that goes into each of them. And so, for instance, anything that adds up to 15, any unique set of your 5 cards that adds up to 15 is, you say 15 for 2, you pay 2 points. And other patterns are flushes, runs. So here we have a run for 4, that would score 4 points. But remember, we're using that flip card. Now, a decently experienced Clojure player will look at that and say, oh, that's a long double run for 10. Okay? Because it is a run of 4, and then a different run of 4, using the other 3, and then the pair. And then a really more experienced cribbage player, we look at those cards and just say 12, because they'd see the 15 for 2 as well. Okay. So scoring a cribbage game, or scoring a cribbage hand, you're looking for flushes of 4 cards or 5 cards, any combinations that add up to 15, you're looking for pairs, runs of 3 or 4 or 1 or 5. And there's also this one odd rule about white jack, where you might have a jack that matches the suit of the flip card, and that's worth 1 point. Maybe his mom is just like that. So it's a British game. It's full of just impenetrable jargon. Now, cricket. Oh yeah, no one understands cricket. They just make it up as they go along. It's basically Calvin ball. So, what would we, if we're doing some card stuff in Java, maybe we're creating an online card server or something to play cribbage online, well, we'd probably start by nailing down some of our nouns, some of our data. We'd say, oh, well, suit. We need suits. Our spades, hearts, diamonds, and clubs. Awesome. And the rank of each card. So we can talk about the ace, the 2, the 3, all the way up to the jack, the queen, and the king. And when counting and looking through those 15s, the 10, jack, queen, and king are all worth 10 points. So you have your rank, but you also have the number of points assigned to that card. And you probably want to put these together into a card. And of course, cards are immutable unless you have a magic marker. Once you have a card, you know its rank and suit forever, unless you're scribbling it out. So we'll make everything final. We'll make the suit and the rank final. And then to my mind, the thinking in Java, if I have a field and it's final and it's initialized in the constructor, I don't really feel the need for a getter. And a setter would be silly if it's a final field. So I just make them public. And people tend not to do that, which I find odd. It's like creating busy work. And of course, toString of card. Oh, okay, I'm going to go code me up a minivan. Yes, so we need a toString because if we're ever looking at one of these or printing one out, it doesn't print like anything. The default printout looks like just a random hash code. So we override toString to identify the rank and the suit. Now, by contrast, the Clojure version looks like that. We want to do a data. We can agree among ourselves that we don't need a type and all these different nouns and noun-specific verbs. We just say, okay, we're going to use keywords, and we're going to identify a rank and a suit. And we're done. Okay. And we're going to build a whole system around a simple data representation. We're going to do that 100 operations around this one map data structure rather than lots of little operations specific to a card or rank or whatever. Now we still need to do things like go from the rank of a card to the number of points for that card. So here we're defining a function for that purpose. Given a rank, and the rank can either be ace, jack, queen, king as keywords, or just the number for numbers 2 through 10. That's what the case function does. It looks at rank and it says if it matches ace, the result is 1. If it's jack, it evaluates the expression 10, returns that. And the final value is the it didn't match default, in which case we're assuming it's 2 through 10 we just return that. So here's how we go from the rank of a card to the number of points. We'll need that when we start looking at how to score 15s. Now, the kind of thing we tend to see in our code is we're chaining together a lot of functions. So we're saying, okay, I have a flip card. That's a map. I'm going to invoke rank on that. Okay, so we're using keyword kind of like a function to extract the rank out of the map. And then we're passing that to points. And we're beginning to see that dreaded thing that everyone's afraid of, lots of parentheses. And it can get worse. If we build this chain up, we're going to have lots and lots of parentheses. And the order is a little bit odd because I look at this and I'm like, I start with the map, and then I do something to it. I pull out the rank, and then I calculate the points. But we have to code it in the wrong order. We say we're going to do the points of something. What's that something? That something is the rank of something. What's that something that we're getting the rank of? It's the flip card. So we have this pattern where we have an expression, and it becomes a parameter to another function call, and then a parameter to another function call. This is very common in Clojure. So there's a way to do that. There's a special macro. We'll talk about the difference between functions and macros later. But there's this thing, the threading macro, dash greater than sign. And it allows you to express it in this order. Start with the flip card. Then we're going to put flip card into the colon rank function call. And then we're going to take the result of that and put it into the points function call. And in fact, on these subsequent function calls, since it knows it has to be a function call, if there's just a single value there that isn't a list, it wraps in a list for you. The end result is we can get rid of more parentheses. These are ones we can get rid of. I know and I care.
Do they require new lines?
No. Clojure does not think about white space whatsoever. So white space outside of quoted strings is entirely meaningless to Clojure. Further, and it's kind of interesting, the comma character outside of quotes is also a white space character. So if you like to do your lists as 1, 2, 3, you're more than welcome to. But the comma actually has no meaning. It just disappears when it's read back in. You can also do key value, comma, when you're doing a map. Some people think it's more readable. I tend to prefer new lines. I've always been a very vertical white space oriented programmer. So I don't like the commas. I prefer to do new lines for readability, but it can all be just a compressed jumble, and it's still the same thing to Clojure. Anyway, what I'm trying to get here is that was a small but a valid little flow. And this is where I know I'm on the right track with my code, when I can push it into this idea of starting with some seed information and going through one transformation after another transformation after another transformation, and then somehow ping at the other end, I end up with my result. I know I'm on the right track. That's the very functional track, chaining functions together, composing functions together to get a desired result. And it plays well with everything else that's going on inside Clojure. Let's get a little more concrete here. What if we're doing a little bit of scoring? So I thought, okay, if I was writing cribbage in Java, what would I do? Well, I'd probably, I'd probably define a data type that represents a score. And a score is going to have a number of points that you scored. 2 points for a pair, 3 points for a run, a description. And I also want to identify the cards, because maybe this is a graphical user interface. And I want to highlight the cards, kind of like I did earlier. I want to highlight the cards to show which cards were used to score which points. Okay, and then I could write one titanic function method that did all the possible scoring top to bottom, and that would just be a nightmare. So, good Java idiom would be to have an interface and use the strategy pattern and have several different implementations of that interface. One that can do flushes, and one that can do the right jack, and one that can do 15s, and so forth. So my intent here is we pass in the hand, and that's the flip card is the first card, and then the other 4 cards. And you're also passed in a mutable list of scores, and if you see a scoring pattern, you create a score object and add it to the scores mutable list. Any number of other possibilities could work just as well. but that's just the way I chose it. Okay, so this is pretty obvious. You could definitely clean this up in a couple of ways, but here's how you score a flush. You look to see if all 5 cards are the same suit, and if they are, it's a 5 flush, and we can add that. And remember, you don't reuse subsets of the cards, so if you have a 5 flush, then you can't score a 4 flush. You score either a 4 flush, which is your 4 cards are all the same suit, or a 5 flush if the flip card matches that suit as well. In fact, I should probably juggle this to look for the 4 flush first. Be that as it may, I look to see if I have all 5 cards of the same suit. If so, I can sort of return early. Otherwise, I do a similar check. So I check the card number 2 against cards 3, 4, and 5. And if those all have the same suit, great, I've scored a 4-card flush. Since we're doing in Clojure, we'll probably define a couple of functions. So flush question mark on the end means that it's a predicate, a function that's expected to return a true value or a false value. So we're saying, is this a flush? And this sort of points out one of the other little differences from Clojure. You notice you can use dashes in the names of symbols, and you can also use a bunch of punctuation. Internally, it does all kinds of crazy name mangling to make things work in Java, but that's hidden from us most of the time. Another thing about Clojure is that you can put a string after the symbol name, and that string is called the doc string, and it's your chance to describe what your function does, and that information is available at runtime. I'll show you in the REPL that you can say doc and then the name of a function, and it'll produce this doc string for you. So that's kind of handy for that exploratory REPL style development. So we have a hand, and we're going to try and determine if they're all the same suit. So let's break this down. Now remember, in Clojure, how do you do something? You use a function. How do you find the equivalent of a local variable in Clojure? You use a function called let. So let consists of a vector in which you have these symbol expression pairs. So we're defining suits and first suit as local symbols that work just inside this let. And we can reference them anywhere inside. So what is suits? Well, we're going to assign suit the expression map:suit hand. Map is one of the main built-in functions inside Clojure. It and it's about 450 buddies are what's inside Clojure core. And map takes some form of collection. This is the minimal case. It takes a collection, applies a function to each value in that collection, producing a new collection. So here, where the function that we're passing is the suit keyword, which says reach into the map and pull out :suit, pull out the value for suit. So here we reduce that choice. We're mapping our cards, which each have a suit and a rank, down to just the suit value. And we're just considering that. Transforming our data. First and rest are generic verbs, kind of like ASOC was. Generic verbs for working with any kind of sequence of values, whether it's a list or a vector or a bunch of other things. First gives you the first element in the collection. Rest gives you all the remaining elements in the collection as a new collection. And next does the same thing as rest, but if you're at the end of the collection, if there's no more values, it returns nil instead of an empty collection. And this is sequences, and this applies to list and map inside Clojure, but also applies to any Java collection, to string, which ends up looking like a sequence of individual characters. Primitive arrays of all types work. Java util map works. So all these different things can act as seeks, sequential objects. And then every, another built-in function of Clojure, it is passed a collection, and it runs a predicate function for each value in the collection, and it either returns true if all the values return true, or returns false if the predicate returns false for any value. So this is our way of saying, are they all the same suit? Is every suit the same as the very first suit, the flip card? And because Clojure is a function language and you're defining functions all the time and passing functions around all the time and returning functions all the time, sometimes it's nice for simple functions to be able to define them quickly and easily. So pound parentheses is a way of defining an anonymous function inline, and that percent is the first argument to the function. So we're saying, feed me each suit in turn from the suits of the cards. Feed me, hearts, spades, and so forth. And return true or false based on whether the first suit, that is the suit of the first card, matches this suit from a later card. So the percent is one value from the suits collection. We see if they're true or false. We see if they match or don't match. And we stop the loop early as soon as we find a non-match. And we return true only if every card passes this equality check. How we do it? Kind of fun? Yeah? What I'm going here in Clojure is this idea that you have a lot of little, small, simple pieces, like these gears, things that you can look at and you can understand how they work. You can see how you could potentially fit them together. But once you have enough of them working together, you can get some really elegant and complex behaviors out of them. And a lot of the genius that is in Clojure is how well these individual pieces, these built-in functions and macros, and the built-in data structures, how well they all just mesh together when you're using the language. It shows some significant thought by Rich Hickey in his hammock. Rich does this whole thing about hammock-driven development. Walk away from your keyboard, hang out in your hammock, and think about something before you commit to code. This shows a lot of that thought and care that Rich put into Clojure for several years before he even told anyone else about it. He was working on this for at least 3 or 4 years before he told another single person that he was working on it. That's pretty impressive. Now that we can look at a set of cards, whether it's 4 cards or 5 cards or 100 cards, and say, is it a flush? We can use that to score a hand. And we say, okay, if the whole hand is a flush, then that's 5 points. And if everything but the first card is a flush, that's your 4-point flush. And we use Clojure's built-in cond, which is kind of like a if-then-else structure, all built together to go to the right value, the right expression. And since we're going to be building these little scoring maps all the time, maybe we'll define a function to make that more concise. And now scoring a flush becomes very concise itself. And once you get past the basic Clojure Lisp syntax, it jumps out at you as very readable. So when the whole hand is a flush, then I'm scoring 5 points. If the rest of the hands, not including the first card, is a flush, then I'm scoring 4 points. I think it jumps out at you in a way that maybe Java doesn't. Mm-hmm. Oh, should I do my Spock talk next? Yeah, so the observation was it looks like Spock, where Spock is a unit testing framework in Groovy, my favorite testing framework, actually. And it has some similar ideas of you sort of work your way down the list and it takes care of things. Yeah. So what about scoring pairs? How would you look at this and find the pairs if you were something as stupid as a computer? You actually kind of blunder your way through it. You compare each possible combination of 2 cards, so that first card, and then against each of its successors, to see which ones have the same rank, but not the same suit. And then you repeat that process for the remaining cards after dropping the first card. And you keep doing this until you're down to 2 cards. In Java, we'll probably use nested loops. We'll iterate over the first 4 cards in the list, cards 0 through 3. And then the inner loop iterates over the remaining cards at each level, and it checks to see if they're identical pairs, meaning same rank. And when that's true, we create a score object and we store it away for later. Okay, now to understand the Clojure solution, we need a little pop quiz. Remember REST? What does REST do again?
Everything but the first element.
Everything but the first element. So here, if we strip off the 1, we get a collection containing 2 and 3. It's no longer probably a vector. It's going to be some other type of collection, but it's still a sequential collection, which means that we can pass it back into REST, and we should get back out 3, and we can get back out of that nil if we were in scheme. Okay, so or if we're using next as our function instead of REST. So in Scheme, which is sort of the modern version of Lisp that isn't Clojure, the empty list and nil are the same idea. So nils are represented as the empty list. So there's no true nil, there's just the empty list. If we feed the empty list back into REST, what do we get? We get itself. Ad infinitum. So, iterate is a cool built-in function. It says, I'm going to build you a collection. I'm going to build you a collection of that value, the 1, 2, 3 you gave me. And then the value in the collection after that is by applying that vector, 1, 2, 3, passing it to REST. We get that out. Then we're going to pass that into REST, and that into REST, and that into REST, and we're going to do it forever. Because in Clojure, all of your main functions that operate on sequences return lazy sequences. Laziness is a virtue. Lazy means computed as needed, as opposed to strict, which means computed all at once. So we can say iterate REST 1, 2, 3, okay, and it will give us back a value representing the beginning of that list. But if we start to print it out, then we've got a problem, because it's going to try and compute that, and it's going to be printing forever. And it's going to be mostly printing that empty list. Okay, so we've got to be careful in our read, eval, print loop not to have it evaluate and print an infinite list. So what do? We use take, another built-in function that operates on seeks, and say, just give me the first 5 from this infinite list. And we see that we get the values we care about and a couple of empty lists at the end. So that's safe, because we're only going to get those 5 values at most out of the collection, even though the collection itself is infinite. Yeah, we can give it a quick try. I'm not quite sure what cursive does, but if we just say iterate, I'll do a different version. Iterate inc1. So inc is increment the value. Let's see what we get. It just hangs. Which is not good. I might have to restart my REPL. Yeah, okay. Okay, so if I instead take 5 from iterate inc1, that returns immediately, no problem. And you can do some other cool stuff. For instance, let's take 20 from iterate from, okay, we'll map and we'll multiply. A map can actually take multiple collections, and those become multiple parameters to your function. So we'll do iterate inc1 and say iterate, oops, sorry, I'm clumsy at this angle. Iterate, say, star2. Okay, so we're creating an infinite list of 1, 2, 3, 4, 5, 6, 7, 8 till the end of time. We're creating an infinite list of powers of 2, and we're saying take all of those numbers from the first list, 1, 2, 3, 4, 5, multiply them by all those values from the second list, 2, 4, 8, 16, 32, produce a new list that's those values multiplied by each other, and then take the first 20 of those. So you might think this will never return, but the way all this laziness works is as the REPL tries to print them, values are computed, and it only goes as far as you actually need, and so this actually does return. Okay. This kind of falls into the simplicity, because you're able to express your algorithms more concisely, because you don't have to worry about how many do I compute at any one time, and do I cache them or do I not, or do I memorize them, or any of that other stuff. That just sort of drops out of the equation. And you get to, it's either simple or focused. You get to focus on your algorithm because you can express it in terms of infinite lists and infinite sequences and not have to worry about a lot of the boundary conditions that you tend to see in traditional imperative code. Given that, let's score some pairs. And look, I fell asleep on my keyboard, and hit all this punctuation. This is where it was. I mean, can anyone remember when they first learned Java? I came from Objective-C to Java, so Java was a bit of a rude awakening for me. This is back in like '97. And prior to that, I was doing PL1. Prior to that, I was in school. So I remember Java looking quite baroque and obtuse to me because I was used to the very precise sort of small talk derived syntax of Objective-C. And it took me a while to code up to the level that I do today. In fact, I'm still getting to be a better, in many ways, more concise Java programmer. Same thing happens with Clojure. Your first pass may not quite look like this. You might find something that's actually harder to follow and more verbose, but easier to understand initially. Or not. I think this is actually not too bad. We're using the for function, which is called a list comprehension. And that's a long way of saying it kind of acts like a for loop or a nested for loop. Okay? So like the let, we're defining new symbols and then evaluating the body of the for. So we're defining a symbol called subhand, which is the hand of cards or the 4 cards after the first card or the 3 cards or the 2 cards. I call that the subhand. And we're actually going to evaluate this subhand once for each value in that expression. Remember, there's our iterate rest hand. And we're saying, take the number of cards in the hand, which is normally going to be 5, but take the number of cards in the hand, decrement it, that's how many we need. And that gives us all 5 cards, then the 4, then the 3, then the 2. So we're going to evaluate past that point for each of those subhands, for the 5 cards, then the 4, then the 3, then the 2. And because this is a very common thing to do, we need to create sort of a temporary value, like a let statement, and you can sort of embed that in the for using this let keyword. That clues in the for function that, we're not defining a new sort of iterating value. We're going to do something that looks like a let statement inline right here. So we're saying left, that's the left card, as opposed to the right card. That's the first card in the subhand. Remember how we compared the first card to the second card, and then the first card to the third card, and the first card to the fourth card. Now we're doing right. We're going over the rest of the cards after the first card, and we're iterating over those. And we only go past this when keyword when they are the same rank. The rank of left and the rank of right are the same value. Only then, when we actually have a pair of cards whose rank matches, do we create a score. And the final result of this for is all of those scores, which maybe none. Maybe there's no pairs. So we get an empty list. Or we get just the scores, just the places where subhand and left and right all matched up. And we get down to that point in the body of the for where we generate an object, generate, in this case, call score to generate a score map. That score map gets returned as a list. Okay, or sorry, any and all score lists that get that far through these nested loops, those get returned as a list. So we're still matching cards, and we're still identifying pairs, and we're still creating scores. Okay, but in many ways, this matches the algorithm that I displayed visually at the beginning more clearly. That we have that triangle that looks like a loop in a nested loop, and again, identifying pairs, turning them into scores, then returning all the scores. Score was a function that we defined a few slides ago, and all it does is take those 3 parameters and convert them into the map that we expect for a score. It has a points keyword and a description keyword and a cards keyword.
So it's predefined. It's predefined somewhere.
We would have to predefine it. We defined it on an earlier slide. So, you've heard the term functional programming. This is all it is. It's data-oriented. It's based on immutability. It probably leverages laziness. But it is a different paradigm. It's a different way of thinking about how things flow through your code. Especially the laziness, which kind of inverts your code. Your code gets called when it needs to be called, not when you said to call it. That can be a little off-putting. Okay, but this I actually took a Dilbert and modified it a little. Yeah, don't share this with Scott. He's a bastard. Okay. So, we're going to talk about macros, which is the way that you extend Clojure in Clojure. And that is really at the pyramid, the peak of the pyramid of power. We're talking about power. And for me, this is all about avoiding boilerplate. I don't like boilerplate code. But in the Java world, sometimes you can't get away with it. I'll give you an example. Inside Tapestry, Tapestry has to do a lot of work, a lot of computations to do what it does. So it does a lot of caching. And to do the caching well, it usually uses a map or something, and it wants to use reentrant read-write lock. Why reentrant read-write lock? Because it's a very efficient lock. It allows multiple readers, which is the normal case when data isn't changing. Any number of readers can grab the read block, and now they have safe access to the data that's being protected, guarded by the lock. But when someone needs to update a value, they can acquire the lone write block. And they'll block for a little while the readers finish their work and jump out. New readers can't come in while someone's trying to get the write block. Eventually, you get the write block. You do your work modifying some internal mutable state. Then you release the write block and you're on your way. But this means every time I try to access one of these guarded values, I need to do a little dance with the reentrant read-write lock. I need to invoke a lock function, method. Do that a lot. I need to invoke a lock function. I need to do a try finally to make sure that I call unlock. Because if I fail to do that, my system will just stop. Because nobody is going to make any progress. No one can take lock if I have to say the write block is left locked. Nothing happens in the system ever again. So you want to get this right, or you'll have a system that fails. So that's boilerplate code, though. I want to have the ability to say, with read lock, here's my reentrant read-write lock, here's a read lock, execute this code inside a try finally that acquires the lock, executes my code, and then with a finally unlocks the lock. That's all I want. Okay? This is actually going to be a little bit easier in JDK 1.8 because the syntax for doing this that currently would involve a lot of infrastructure and interfaces and inner classes and garbage like that is going to shrink down. And so this kind of thing's actually coming in JDK 8, and we'll be able to do something that looks a bit like this pretty soon, and that's kind of cool. But even that's still a ways off, and it's still not quite the same. It comes down to, I want to put this feature into Java. Who owns Java? It could be this guy. It's Mark Reinhold. He's like the top technical guy for all things Java at Oracle. So he is the guy who reports to the Oracle Big Brass about what's going on with Java. Day-to-day, it's Brian Getz. So Brian Getz would be smarter than everyone in this room combined, and also in a really vicious poker player. And his job is to say no about 99% of the time. You have a cool feature that would give you a huge advantage in writing your Java code. His job is to point out to you why it's a bad idea, because it breaks backwards compatibility or causes some other subtle problem that only people who are developing Java, including him, can really fully appreciate. Because he's thinking not in terms of you, not in terms of me, he's thinking in terms of hundreds of thousands of Oracle Java developers who would not like it if their language broke up. Okay, so his job is to say no. The short of it is not you. You don't own Java. In order to do the change I just described, again, JDK 1.8 makes the syntax a little more palatable. But to do it right, you'd have to hack the Java compiler, and you don't own the Java compiler. And even if you forked open JDK and said, hey, everybody, come over to my pool, I've got this cool new feature in Java, you're going to have a hard time convincing IntelliJ, NetBeans, Oracle, all the major players who have to adopt your change to take it back and make it public. I mean, if you did, you really couldn't deploy code for other people that used your new feature until all of them had done it, and that's years in the making. So we don't own Java. We play in their sandbox, and we don't get to do it. But welcome to the head exploding zone of all Lisps. Because the key feature of Lisp is how much Lisp is implemented in Lisp. Remember what the reader does. The reader reads characters and turns them into forms. And you have literal forms like strings and nil and numbers. You've got the vectors, the lists, the maps, the sets. But you also have things that look like function calls, parentheses, and then you have, the symbol you want to invoke and then parameters. And this includes normal functions, but also a special kind of function called macro. When the Clojure compiler is operating, remember it operates all the time, okay? Whether it's read eval print loop or reading Clojure source from a file, at runtime the Clojure compiler is reading and evaluating, and part of the evaluation is bytecode generation for functions. It sees all this macro expansion. So it sees macros, and macros, as we'll see, break apart complicated forms into more verbose, simpler forms. And so you get down to these, a limited number, I think in Clojure it's about 12 special forms. These special forms are the parts that are actually built into Clojure. Everything else builds off of them. They're kind of the DNA of the language. And it's only those 12 or so special forms that the Clojure compiler recognizes and can turn into bytecode. So everything else you do in language is typically going to go through some number of macros and go from tight little code to fairly verbose code. But you know what? That's a lot like what happens in a traditional compiler, where a traditional compiler reads characters, lexes them into parse trees and abstract syntax trees, and then all sorts of different intermediate representations, and keeps working on this until it gets down to stuff it can turn into bytecode or assembly code or whatever the output is. Clojure is doing the same thing, but tends to do it at runtime. And macros are the mechanism for this. The end result is you don't have to wait for Rich Hickey to do it. You don't have to wait for the Clojure team to do it. Almost anything they can do to the language, you can do to the language right now. Okay. So maybe I have a Clojure function that's going to check my cache. So I pass in a key, and I say, okay, with read lock. So I don't know what with read lock is yet. We'll talk about what with read lock is in a second. I'll code it up for you. I have cache lock. That's my reentrant read-write lock that I have, again, floating around in a symbol ready to use. And then I have some function that is unsafe. And the convention here is an exclamation point at the end represents some form of unsafe operation, one that blocks or does some kind of mutable change to some existing value. Use the exclamation point. So I'm saying I'm reading from the cache, but it's dirty, it's unsafe. I need to make sure I have a read lock in place. What I want is with read lock to convert into this. I'm going to get my cache lock, and I'm going to do something to it. I'm going to do the lock on it, and then I'm going to do that read from cache, and then I'm going to have a finally block that does the unlock. So let's see what that looks like. Okay. So first, I'm going to import reentrant read-write lock. Okay. Great. So now I've imported that. And if I want, I can create a reentrant read-write lock. This is part of the Clojure interrupt syntax. A period at the end inside what looks like a function call is a new. So this is new reentrant read-write lock. And you can see it prints it out and do that, oops, down to the end. And you can see that has write lock 0, read lock equals 0. So no readers, no writers, we're ready to go. Okay, cool. Now, what I want to do is something kind of like this. I'm going to say, okay, I want the read lock And the way you get that is we're going to start, oh, first I need to lock itself. So and again, if I print out my lock, what I get is that lock instance, and it shows 0 read locks, 0 write locks. Now what I want to do is this. Dot read lock of my lock. Okay, and then I'm going to lock the read lock. So again, more interrupt syntax. You can call methods on Java objects by using dot and the method name, and then passing the object that you want to invoke as the first parameter. So internally, it turns this around and says, hey, it's a Java object. I'm going to invoke the lock method on it. Then, with that lock in place, I'm going to print out the print line, the lock, and then finally unlock the read lock. So if I've done all that correctly, apparently I didn't. Oh, I forgot my try. So we'll put a try here, and we'll bring in that and that. Okay, so you can see that I create a local variable for the read lock. I lock it. I print it out to show that the read lock's value is 1, and then I unlock it at the end. And now if I print out my lock, it's back where it started with no locks. No read locks, no writes. Okay, whew. That was a bit of typing. Okay, that's more than I want to type. But we can create a kind of template for that in our language. I'm going to do it quickly here, and then I'll discuss in more detail on the slides. The template's called a macro. And it's going to be called with read lock, and the first parameter